Mastering metaheuristic optimization algorithms in modern problem-solving. The field of optimization has evolved dramatically over recent decades, driven by the increasing complexity of problems faced across disciplines ranging from engineering design to financial forecasting. As traditional deterministic methods struggle with high-dimensional search spaces and non-linear constraints, metaheuristic approaches have emerged as powerful alternatives that balance exploration and exploitation effectively. These intelligent search techniques are particularly well-suited for tackling NP-hard problems where exact solutions become computationally prohibitive. By mimicking natural processes through stochastic mechanisms, they offer practical solutions within reasonable timeframes while maintaining robustness against problem-specific variations. Understanding the core principles of metaheuristics at their foundation, metaheuristic algorithms operate through iterative improvement processes guided by heuristic rules rather than strict mathematical formulations. This flexible framework allows them to navigate complex solution landscapes without getting trapped in local optima. The key distinction between classical optimization methods and metaheuristics lies in their approach to searching for optimal solutions. While gradient-based techniques rely on precise derivative information, metaheuristics utilize probabilistic strategies that enable them to escape shallow local minima and explore broader regions of the solution space. This adaptive nature makes them particularly effective when dealing with multimodal objective functions characterized by numerous peaks and valleys. The ability to dynamically adjust search intensity based on current findings is what gives these algorithms their remarkable versatility. In practice, most metaheuristic implementations follow a common structure involving initialization, evaluation, selection, and perturbation phases. These stages form an iterative loop that continues until predefined stopping criteria are met, ensuring computational efficiency even for large-scale problems. Initialization generates diverse starting points across the solution domain using random sampling or Latin hypercube designs. Evaluation computes fitness values based on target objectives using custom-defined evaluation functions. Successful implementation requires careful calibration of parameters such as population size, mutation rates, and neighborhood sizes. These settings significantly influence convergence speed and final solution quality, making parameter tuning a critical aspect of algorithm configuration. One crucial consideration is balancing exploration versus exploitation tendencies during the search process. Too much emphasis on exploring new areas can lead to slow convergence, whereas excessive focus on exploiting known good regions might prevent discovery of better solutions elsewhere in the landscape. Evolutionary computation techniques. Genetic algorithms represent some of the earliest and most influential metaheuristic approaches inspired by biological evolution principles. Through operations like crossover, mutation, and selection, they simulate Darwinian survival of the fittest dynamics to evolve better solutions iteratively. The basic GA workflow involves creating an initial population of candidate solutions, evaluating their fitness according to specified objectives, selecting individuals for reproduction based on performance metrics, and applying genetic operators to generate offspring for subsequent generations. Crossover operations combine features from two parent solutions to create novel combinations, often resulting in improved offspring with characteristics inherited from both parents. Mutation introduces small random changes to maintain diversity within the population and avoid premature convergence. Selective pressure plays a vital role in directing the evolutionary process towards promising solution directions. Tournament selection, roulette wheel selection, and elitism strategies help maintain appropriate levels of competition among candidates. Variants like differential evolution extend the GA paradigm by incorporating vector differences to guide mutations systematically. This enhancement provides more structured exploration capabilities compared to simple bit flip or Gaussian mutation schemes. Hybridizing GAs with local search techniques creates mimetic algorithms that integrate global exploratory power with local refinement abilities. This combination helps achieve faster convergence without sacrificing solution quality. Parameter setting remains a significant challenge in GA applications due to sensitivity to various factors including population size, crossover probability, and mutation rate. Adaptive parameter control strategies have been developed to address these challenges automatically during runtime. Swarm intelligence approaches particle swarm optimization takes inspiration from bird flocking behavior to model collective decision-making processes in decentralized systems. Particles representing potential solutions move through the search space adjusting velocities based on personal best experiences and swarm-wide knowledge. The PSO algorithm maintains velocity vectors for each particle that dictate movement direction and magnitude. Velocity updates incorporate cognitive components reflecting individual learning and social components capturing swarm intelligence. Velocity update equations typically involve inertia weights, cognitive coefficients, and social coefficients that determine how strongly past velocities influence future movements. Tuning these parameters affects exploration-exploitation balance critically. Convergence acceleration can be achieved through dynamic adjustment of inertia weight values that decrease linearly over iterations. This strategy enhances early-stage exploration while promoting focused exploitation later in the search process. Modified versions like Comprehensive Learning Particle Swarm Optimizer enhance standard PSO by allowing particles to learn from multiple exemplars simultaneously rather than relying solely on personal/global bests. Multi-objective extensions of PSO handle Pareto front identification by tracking trade-offs between competing objectives. Dominance relations and crowding distance measures help maintain diversity in the archive of non-dominated solutions. Applications span mechanical engineering design optimization, economic load dispatch problems, and neural network training scenarios where parallelizable computation architectures provide advantages. Ant colony optimization strategies. Ant colony optimization draws from observed ant behaviors where colonies collectively find shortest paths through pheromone trails laid down by previous travelers. This bio-inspired method applies similar principles to solve combinatorial optimization problems efficiently. Artificial ants construct solutions by moving through graph structures representing problem domains. Pheromone deposits left behind serve as indirect communication channels guiding other ants' decisions in subsequent iterations. The amount of pheromone deposited depends inversely on path length, reinforcing shorter routes over longer ones. Evaporation mechanisms ensure that outdated information doesn't dominate the search process indefinitely. Pheromone update rules include both local updates performed after each step and global updates applied at regular intervals. This dual mechanism balances memory retention with adaptability requirements. Elitist variants give extra pheromone reinforcement to the best performing solution found so far, helping direct searches toward globally superior options. Parallel implementations allow independent ants to explore different regions concurrently, accelerating convergence speeds significantly compared to sequential execution models. Hybrid ACO frameworks integrating local search heuristics demonstrate enhanced performance on challenging benchmark problems featuring deceptive landscapes and multiple local optima. Simulated annealing methodology. Simulated annealing emulates physical annealing processes in metallurgy where controlled cooling schedules reduce material defects. It uses temperature-dependent acceptance probabilities to gradually refine solutions approaching optimality. The algorithm begins with an initial solution state and explores neighboring states according to a defined transition probability distribution. Acceptance of worse solutions depends on the current system temperature and difference in solution qualities. A carefully designed cooling schedule dictates how rapidly temperature decreases over time. Slow cooling increases chances of finding near-optimal solutions but demands more computational resources. Adaptive simulated annealing techniques modify cooling rates dynamically based on progress monitoring indicators instead of fixed schedules. This flexibility improves efficiency without compromising effectiveness. Variations like threshold accepting replace continuous temperature variables with discrete thresholds determining when to accept inferior moves, simplifying implementation complexities slightly. Taboo search incorporates memory structures to avoid cycling through previously visited solutions, complementing essays' probabilistic aspects with deterministic elements for more systematic exploration. Combining SA with other metaheuristics forms hybrid systems capable of handling complex optimization tasks requiring complementary strengths from multiple methodologies. Benchmarking and performance evaluation. Comparative analysis of different metaheuristic algorithms relies heavily on standardized test suites containing diverse classes of optimization problems. Common benchmarks include unconstrained, constrained, single-objective, and multi-objective function sets. Performance metrics typically evaluate solution quality, convergence speed, consistency, and robustness across multiple runs. Statistical tests like Wilcox and signed rank tests assess significance of differences between algorithm performances. Diversity measurements quantify how spread out populations remain during searches, indicating whether algorithms prematurely converge to suboptimal solutions or maintain adequate exploration capacity. Computational time comparisons reveal which algorithms scale better with increasing problem dimensions. Parallel processing capabilities also affect overall efficiency assessments significantly. Visualizations such as convergence curves and solution distribution plots aid in interpreting algorithmic behavior patterns. These graphical representations highlight characteristic traits like fast initial improvements followed by plateaus. Algorithm rankings derived from benchmark studies inform practitioners about relative strengths and weaknesses under varying conditions. However, results may vary depending on specific implementation details and parameter configurations used. Emerging research focuses on developing automated algorithm selection tools that recommend suitable optimization strategies based on problem characteristics identified through feature extraction techniques. Current trends and future directions. Recent advancements emphasize integration of machine learning techniques with traditional metaheuristics to enhance predictive capabilities and automate parameter tuning processes. Reinforcement learning shows promise in optimizing control policies governing search trajectories. Surrogate modeling approaches leverage response surface methodology to approximate expensive to evaluate objective functions, reducing computational burdens associated with repeated evaluations required by many metaheuristics. Quantum computing concepts inspire new algorithmic paradigms that could potentially revolutionize optimization problem solving. Quantum-inspired evolutionary algorithms already show encouraging results in certain application domains. Cloud-based platforms enable distributed execution of metaheuristics across geographically dispersed nodes, facilitating massive parallel computations essential for large-scale problems requiring extensive resource allocations. Explainable AI initiatives seek to make black box optimization procedures more transparent, addressing concerns regarding interpretability of complex algorithmic decisions made during search processes. Sustainability considerations drive development of energy-efficient optimization algorithms suitable for deployment on low-power devices without sacrificing performance levels appreciably. Ongoing research investigates ways to embed ethical guidelines into algorithmic decision-making processes, ensuring responsible usage aligned with societal norms and regulatory requirements. Conclusion: metaheuristic optimization algorithms have proven indispensable in addressing modern-day complex optimization challenges spanning various scientific and industrial fields. Their ability to handle highly nonlinear, multimodal, and constrained problem instances makes them uniquely suited for real-world applications. To harness their full potential, practitioners must develop a deep understanding of underlying principles, algorithmic intricacies, and application-specific nuances. Careful parameter tuning combined with strategic choice of appropriate algorithm families ensures successful implementation outcomes.